Okay, so welcome to the class again. I hope it's visible. So, okay. Otherwise, I can also turn it off. Do you prefer to turn it off? Okay. All right, so right, video recording reminder. So I'm recording. And there's going to be a tutorial today after the lecture. It's going to be about the Q&A session for exercise 1 by Alex. And yeah, there is another reminder for course evaluation. So I think for those who provided the university email address, you should have got the survey or some evaluation form. I heard that the current completion rate for this course is pretty low, so I'm kind of required to kind of remind you again for this evaluation. So yeah, if you wish to do it, then yeah, please do it. Okay, as soon as possible. I don't know when is the deadline exactly, but yeah, do it today or yeah. There has been a lot of errata and actually needed clarification for the previous lectures. Yeah, it's a shame, but looks like there are some needed clarifications for, let's say, terminologies for the OOD generalization part. For example, like terminologies like OOD, domain, cross-bias generalization. These are kind of eventually a little bit mixed up together. So maybe next time I can spend a bit of time on clarifying what I mean by each of them. And also from the last lecture, there has been like different senses of the meaning of words like local versus global, or what I exactly mean by linear. So all of these I will clarify in the next lecture. The reason I'm trying to do that next lecture is if you have any other questions or requests for clarification, then please send me an email before next lecture, and then I'll try to explain in detail. Okay. And with that, let's move on to class activation maps. Yeah, this is another clarification because I was kind of rushing a bit in the last lecture, so I'm going to explain a bit more on the equivalence of CAM formulation and so on. Okay. So class activation maps. Yeah, I want to kind of get rid of it, but it's impossible. So this is the general, right? I'm probably going to skip all these slides because I have better visualization. Yes.
Last question for this slide.
Oh, okay.
At the point where format, like when I think about the other slides about CAM, isn't the score map like at this point actually still like multi-channel?
Yeah, it is. Yeah, yeah. So yeah, this is a huge simplification. So probably it's better to, yeah, so these are all slides from last lecture, and then I finally made a better visualization of everything. Okay, so now don't think about the previous crappy figures and just look at this one. So this is the usual output from layer 4 of ResNet 50. So you actually have two 2048 dimensional panels here, and your resolution at this point is 7x7. It's very, very low, and it actually can't really tell apart different locations in the image pretty well. It's quite hard for the model to do that, but yeah, it's probably fine. And then what happens is you do global average pooling, meaning that you're taking the average across the spatial dimensions for every channel. Okay, and then you have two 48 dimensional vector, and then you have an FC layer, meaning that you're just multiplying a matrix on top of this vector. And then you're eventually going to get 1000 dimensional vector for classifying ImageNet images, because ImageNet 1K has 1000 classes. And how you compute CAM out of this network is a little bit complicated, and I'm not happy about that. So what you do is, first of all, you take the weight for the class of interest Y. Okay, so that's going to be one of the rows in this matrix. And that's going to be a 2048 dimensional vector. You just take that out and then do the average pooling of your layer 4 output according to the weights in this 2048 dimensional vector. And that's going to give you a 7x7 map describing where is the object. Okay, that's your CAM. But if you have to do it in PyTorch framework, then you have to kind of first search for the layer called FC, and this is already not a very nice way of addressing a parameter or a variable in your Python code. And then you take this weight and then data, and then you take the slice, and then you do unsqueeze here. Yeah, I actually missed 2 more unsqueeze operations here. So there should actually also be unsqueeze for dimension 2 and then unsqueeze for 3. After doing that, you can kind of do the broadcasted multiplication with the with the x right here, and then you take the sum, and that's going to be your CAM. And to me, to my taste, this is way too complicated. And the way to make it simpler is to consider this mathematically identical way of writing things, or way of computing things. So you have the same shaped layer 4 output here, but instead of doing global average pooling first, you sort of do the FC layer first. But you know, FC layer can only be applied to a vector rather than a tensor, right? 3D tensor. So you have to turn this FC layer into something that could be applied to a feature map, a 3D tensor, but with the same operations at every feature pixel. And that's exactly what one-by-one convolution is doing, right? So instead of nn.linear, you take nn.conv2d with kernel 1. Okay, so that's also encoded by 1000 times 2048 dimensional matrix. So you have the identical weights actually for these 2 operations. And by applying this one-by-one convolution, you're going to have instead, you're going to keep all the spatial dimensions, but turn those 2048 dimension into 1000 dimensional 3D tensor, and then do global average pooling. Yes?
Would this still work if it was global max pooling, or no?
No, it's not going to work for global max pooling. It's working here because these are linear operations, and so you can, it's commutative. Yeah, I'm not sure if you can call this commutative. It's more about associativeness of the operations. Yeah. Mm-hmm. So how to implement the second model? It's quite simple. You just take convolution, 2D convolution on top of the layer 4 output, and then you do average pooling, global average pooling, and you have the same shaped vector as before. I call this fully convolutional ResNet 50. And this kind of fully convolutional network has been used a lot for, in the era of CNNs, for semantic segmentation, because you kind of need to keep all the spatial dimensions all the way up there. And then eventually what you're training is the pixel-wise prediction for the class. Okay, so you actually needed this kind of tensor as an output of the network to train this segmentation network. But nowadays, a lot of people are using transformer-based baselines for doing semantic segmentation as well. And then the practice is kind of a little bit old-fashioned now. Okay, and now the question is, how do you compute CAM in this case, right? And computing CAM is way simpler here, because what you have to do is just to take width channel in your 1000 dimensional channel 3D tensor. You don't have to multiply with anything. You just take this score map and that's your cam. Yeah, so you just take the slice here. So a strong pro here is that it's much simpler implementation, at least in my taste. In my numerous previous experiments, I have confirmed many times that it gives the same classification accuracy. So yeah, it's not only mathematically the same, it's also implementation-wise the same. You're never sure if the implementation is the same as the mathematical, even if there's mathematical identity, because you don't actually know what's going on in the CUDA backend or PyTorch versions and so on. So it's still needed to kind of confirm this, and yeah, we are fortunate that this is confirmed in this case. Okay. One minor con is that it's using a little bit more memory during training and inference, because instead of 2048 dimensional vector here, you now have 49 times 1000, 49,000 values here. So that's slightly more memory usage, but compared to the total memory usage for a deep network, that's negligible in my opinion. So it's good. Okay, so I hope that was clarifying this better. Okay, so let's now look into what is required by CAM to make it work. Because yeah, the first point is that CAM is also relying a lot on linearity, or it's kind of a version of linear function as well. And the linearity for CAM is hiding here in the spatial pooling. You'll find the results is eventually just the average or the sum of your individual features at every feature map pixel. Okay, so in that case, your final prediction can be kind of split into the predictions from each of the feature in your feature map. Okay, so that is very interpretable. It's just a sum, and for sums, people have a very good intuition of who's contributing how much and so on. So we're kind of taking advantage of that, which is good. But actually, one caveat here is that there's a crucial assumption to make CAM work. Okay, so that is the fact that okay, you're kind of treating each feature pixel in the score map as the actual features from the same corresponding location in the input image. Okay, this is kind of empirically found to be true for CNN models, because CNNs are kind of translation invariant, and therefore there is also a notion of receptive field for every pixel in the feature map. So for every feature pixel in the score map, you kind of trace it back to the possible range of pixels in the input image that could make some impact in the current feature pixel. And that tends to be a huge kind of receptive field, right? And that is also kind of moving with the location in the feature map. So if that does not actually hold, then you cannot really trust CAM, right? Because even if your feature map looks like this, maybe this region with a high attribution score correspond to another like completely different location in the input image, right? So that is a strong assumption, but so far it has been working. This assumption is kind of broken for transformer-based models because they do not enjoy the same kind of translation invariance. And so it's unclear whether the token values, the token-wise features, after all the self-attention layers, actually convey the same semantic content as the corresponding tokens at the beginning. Although, yeah, I've seen work where Yeah, I'm not entirely sure about that. Yeah. Yeah, I'm still looking for papers proving this or disproving this. Maybe there are papers on that, but I'm not sure. Yeah, this is the point. For VITs, maybe this doesn't work anymore. Well, the VITs mean visual transformers. Okay. And now again, there was a linear mapping here, and we took advantage of that. But the question is, what if that part was not linear anymore? And that was the question that the GradCam paper had, which is the follow paper on CAM. Okay. So actually, as we have seen from the previous lecture and so on, a quick way to turn a non-linear mapping into a linear mapping is to take a gradient. So what GradCam is doing is eventually just turning this nonlinear rest of the parts into a linear mapping by taking the gradient. So yeah, this is the figure from GradCam. It's kind of hard to interpret what's actually going on, but I'll try to explain. Okay, so you have sort of fully convolutional network here first. So you're going to get some sort of feature map here. Okay, so that's the same as previous setting, but now you have a second part of the model which is not necessarily linear anymore, and for example, that could be if there are more than more than one FC layer, then it's nonlinear anymore, right? So it's a good example of a network where the CAM is not working anymore. A good example of that was actually VGG network, because after convolutional layers, they had 3 more FC layers. So these are nonlinear, and CAM was not really working for VGG a priori. The other example is, for example, image captioning. Nowadays, no one is doing LSTM RNN for generating a caption, but these days, for those times, yeah, that was kind of the standard method. And of course, it has a lot of non-linearities in between, so it's not differentiable. It's differentiable, but it's not linear. And visual question answering as well. So whatever complicated stuff you have here, as long as that is differentiable, you can linearize it around the input of interest, okay? So let's say this is A, and A is like the 2048 dimension times 7 by 7 feature, for example, okay, that we have seen before. And yeah, exactly. It gets a little bit more complicated now. So first of all, what you do is you get the gradient with respect to those 2048 times 7 by 7. And then you take the average of the gradient, which we call alpha CK. So that is the gradient of the class C with respect to this channel dimension K among those 2048 dimensions. And then you actually do spatial pooling of those activation gradients. And then it gets even more complicated. You take the weighted average of your activations according to this averaged weight, alpha CK, okay? They also do some ReLU here, but I don't think, yeah, I don't know why they put it as ReLU, because, yeah, the original CAM is anyways doing max normalization, meaning that they drop all the negative values and just normalizing with the max value anyway. So, yeah, yes.
So C corresponds to the class dimensionality. So, for example, 1000.
Yeah.
And K is this intrinsic dimensionality, right? So, so the alpha could be deemed as a matrix 2048 times 1000.
Yeah. But typically, you just choose one C, so it's more like a vector rather than a, yeah. And if you write everything together, it kind of looks like this. So you take the gradient of YC for a class of interest C with respect to A, K, I, J, right? So these are all individual members of your attention. So you take the gradient like this, and then you take the average pooling. So IJ dimensions are spatial dimensions. And then you're also kind of summing over K dimensions here with the original attention value. And there's H and W, which is the pixel index for the final cam that you wish to get. Okay, so the message here is that it looks complicated. I also find it very complicated, and I don't have a good explanation of why they do it. And yeah, I still don't know why they do it. It's the truth is this is actually a generalization of the original cam, in a sense that if you just have a linear layer, then you're going to have this the weights here for weights for the linear layer, and you get the original cam formulation back. But yeah, still, to be honest, I don't know why they took gradients instead of, yeah, I don't know what is a good solution here, but yeah, it happens, right? Sometimes they do it and it becomes super popular, but still there are people who are kind of left behind and trying to understand why they do it and why people like it. But yeah, they say it works well. And they actually also refer to CAM as grad CAM in many cases, because grad CAM is a generalization of CAM. Okay, so when you see grad CAM in some papers, that could actually just mean CAM. Okay, with the linear layer on top of your feature map. All right, so that was grad CAM. It's still good to know what grad CAM is, right? So, and there are some remaining weaknesses that I wish to also talk a bit about, which is that CAM is not very interpretable. Well, the function that's on top of the feature map was just linear, just averaging. And so I said that is very interpretable, but that's not the end of the story, in my opinion, right? I'm going to explain why that is the case. So after fixing the formulation, now we just have a feature map, and then you have average pooling, and then softmax. This is the fixed formulation. Very nice and neat way of training a fully convolutional network. But then at test time, or more when computing CAM, what you do is a very complicated, it's not very complicated, but some random normalization step, okay? It's not very well motivated, that's what I mean. So you take this feature map first, right? It's going to be three-dimensional tensor, right? And then you throw away all the negative values by taking max with 0. And then you're actually normalizing, linearly scaling down to the 0, 1 range by dividing by the max value of the CAM score map. Of course, it's needed to kind of scale everything down to 0, 1 range, right? Because otherwise, there's no way you can compare your score map consistently across many images. So there should be a fixed range of possibilities for your score map for sure. But the thing is, if you just look at this pre-softmax values, they're not automatically within some range, right? So there should be a mechanism for kind of scaling them back to more interpretable, calibrated range, which is to say, let's say 0 and 1 range, okay? Some people also do min-max normalization. So instead of throwing away all the negative values, you make sure that the mean value becomes 0 value and the max value becomes value 1, okay, through some linear transformation. And if you try to explain what is happening in English, it's like it's the pixel-wise pre-gap, pre-softmax feature value at HW measured in relative scale within the range of values 0A, where A is the maximum value of feature values in the entire image. And imagine like you're explaining this to an end user who has no idea of what machine learning is and so on, right? They're not going to understand what's shown in the score map. So we try to fix that. So yeah, briefly explaining what the problems are. So the test computation graph is not part of the training graph. That's the problem. Because then we are kind of making up values later at test time for generating those score maps. Yeah. And so to fix that, this is actually one of our papers before. So it's called Class Activation Latent Mapping, CAM. And we build this kind of probabilistic graph first, where X is the input image, Y is class label, and Z is pixel index. I'm not sure how many of you are familiar with probabilistic machine learning. I hope people know the basics of like the probabilistic graphs and latent variable models and so on. Yeah, okay. I see some nods and okay. All right, so let me know if something is not very clear. So you have the same kind of ingredient first, right? So given an image, you have fully convolutional network, and then you're going to get some intermediate feature map, right? So far we have the same kind of formulation as CAM, but afterwards we wish to predict a joint distribution of Y and Z, where Y is the class and Z is the location. I didn't explain what this is, right? So class label is a discrete random variable, and pixel index is also a discrete random variable in the feature map dimensions. So it's, for example, from 1 to 49 for 7x7 feature map. And the interpretation in human language is we're going to predict the final class Y from the image X by looking at pixel Z. Okay, so our prediction is based on the observations at the feature location Z in the feature map. And we call this latent because Z is not observed. Only X and Y are observed, and therefore the training set is just the same, right, as training a classifier. You have X and Y samples and train the whole thing, but without ground truth labels for Z, okay? And the first part is to get a joint distribution of Y and Z for Y and Z. Because Y and Z are discrete random variables, you can fully represent the joint distribution through a matrix of Y and Z. But here Z is, again, a spatial location, so it has 2 dimensions, and therefore we have 3-dimensional tensor, okay? C for the classes Y, and W and H for the location Z, okay? And the only requirement for this to be a joint distribution is that it should sum to 1, and the value should be between 0 and 1. And we kind of enforce that through all kinds of normalization here on top of the intermediate feature map, and everything is differentiable. Okay, so now that we have this nice ingredient, which is a joint distribution of Y and Z for every pixel, right? We have 3 phases now. One is testing phase, right? And here, like in CAM, we just need to do global average pooling on top. And that's going to give you a marginalization of Z out. And that's going to give us the probability of Y given X. And that's exactly what we need to predict the class. Now for interpretation of where the object is and so on, like in CAM, we just need to take the ground truth y from this tensor, and that's going to give us calm attribution. The nice thing here is that this attribution is now well calibrated between 0 and 1. Okay, unlike CAM. And now how to train this? So there are two ways of doing it. So marginal likelihood way of doing it and expectation maximization way of doing it. So these are two typical ways to train a latent variable model in machine learning. I don't think you need to know all the details of what is marginal likelihood for understanding this and expectation maximization. I'll try to explain intuitively as much as possible. So what marginal likelihood does is first, like in testing phase, you take you marginalize Z out by averaging through the spatial dimensions, and then you're going to get a prediction, and you can just train it, right, using negative local likelihood, like cross entropy loss. Okay, that's called marginal likelihood. Fancy name, but that's just you average and then you train it. There's also expectation maximization. If you know some work in segmentation using CNNs and so on, then probably this looks a bit more familiar because this is exactly how you train let's say, deep lab model for using pixel-wise ground truth masks and then training this 3D tensor based on that. So I'll explain what I mean by that. So you have this joint distribution, and then based on that, you get a joint likelihood. This is now likelihood because you're kind of applying your knowledge of what is the true y here. So you're taking the slice basically for y. And then you make sure that this slice sum to 1 by normalizing with the sum of the values here. And in probabilistic notations, that's just P of Z given X and Y hat. And that becomes your pseudo target for your joint distribution. Okay, so now what I mean by that is this target. Okay, so it's like pixel-wise negative log likelihood loss between this joint distribution and pseudo target. So for every pixel in the feature map, you're going to have a full kind of prediction vector here, and then and then here you expand this value here into a one-hot vector. Okay. Where y dimension is taking value in this matrix, and all the other channel dimensions are taking value 0. Okay, and with this vector, you can actually train this joint distribution with pixel-wise cross entropy loss. So that's what's happening here. And this is equivalent to what people say expectation maximizations. An important detail here is that you should detach here. Yeah, that is kind of derived from the expectation maximization algorithm. So given that, now we have a simpler way to compute explanation square map from your model. You just take the slice, right, as before. In English, it's the probability that the Q for recognition was at pixel Z, and the ground truth class Y hat was correctly predicted for the image X hat. Okay, so to me, at least that's simpler than CAM. Yeah. And there are some windfall gains, I would say, for CAM attributions, score maps. For example, when a value is well calibrated and probabilistic, you can do a lot of derivative calculus, like derivative computations on top of it. For example, you can kind of sum up the attribution for all possible classes for this image. And that's what you're going to get, P of Z given X. Because let's say you marginalize out Y from this kind of all possible attributions for all the classes, right? Then P of Z given X is going to be the attribution of any class that you're interested in. Let's say for ImageNet, that's going to be 1,000 classes. And where's any object that belongs to those 1,000 classes in this image. And still, this is a nicely normalized, nicely calibrated 0 to 1 range values on the image. You can also take a subset of the classes to sum the scores up. For example, there are more than 200 dog classes for ImageNet. So if you actually sum up the score maps for dog classes in ImageNet, then you're probably going to get a better delineated boundaries for the dog class than before. You can also subtract different score maps and still get a score map that still makes sense. Okay. And so we try to do something similar, like, for example, subtracting the score maps for CAM, for example. But the point here is that we are getting better score maps than CAM with CAM. Okay, so since I didn't really talk about evaluation metrics for explainability yet, I'm probably going to skip this slide. Okay. Yeah. So this is a quantification of the slide before. And it kind of shows that compared to CAM, ours is better. Yeah, again, this is called remove and classify attribution evaluation. So I'll explain better after a few slides. Okay. But the point here is that CAM is performing better than CAM, for example. And also compared to other attribution methods like input gradient, smooth gradient, and so on. Yeah. One caveat is that there is some cost to pay because CAM is actually changing the network structure. So it's now very different from the reformulation of CAM, right? Because before, for reformulating CAM, we had the same function as before and train the same kind of model. But now if you change from the original network structure to something that is following CAM formulation, then you're actually changing the mathematical structure of your model. And so you cannot expect the same level of accuracy as before. And so let's say your original model was ResNet50, and this is fully compatible with CAM. But now when you change that to CAM, then actually you're losing a few points, right? Like 4% points for ImageNet. For CUB, you sometimes gain and sometimes lose a lot, actually. So you should be careful about these kind of possible losses with CAM. So it, to me, this looks like there's some trade-off between interpretability and model accuracy. And the existence of trade-off is very interesting because because that also means depending on your actual needs, you might need to choose a different model. For example, there can be applications where losing like 4% points is not as important as gaining confidence in the way the model is working, right? You're just losing 1 out of 25 samples. And at the cost of that, you're gaining a better picture of what the model is doing and so on. For those kind of applications, then you probably need CAM trained models. So in general, I think having these kind of diverse requirements for deployment means we need to develop more diverse types of models. So we should not really just aim for models that are performing well on the validation set, but probably also develop slightly suboptimal models that are still interpretable or generalizing very well to unseen situations and so on. So, yes.
Could you maybe provide some intuition on why should such a trade-off exist, or why does it exist at all? Because it's actually not intuitive why they should be trade-off.
Yeah, because okay, so if you're kind of confined to interpretable models, then you're kind of limiting yourself to a smaller fraction of models to be considered, right? And also that's also kind of binding yourself to human understandable mechanisms. And it looks like for, let's say, image recognition, there are mechanisms that lets models recognize well, which are not fully aligned with human way of doing it. Yeah, hope that answers, right? And I think that's very important point. So I think that's exactly where we have choice, whether we just trust the model and let it, because it's working well, we just use it, or if at the small cost we pay, we still wish to make it recognize things as humans do. Okay. Yeah, I think both are important in different applications. Right, so this is the disclaimer. I still actually think CAM is a great attribution method, but if you're considering CAM, then probably you should also consider CAM. Okay. Maybe these will be the last slides for the first session, and then we take a break. So there are also methods that I did not actually mention in this course. There are modified backpropagation variants like layer-wise relevance propagation, deep lift, deep sharp, guided backpropagation, excited backpropagation, and nowadays for transformers there are also like GAE or just input times gradient, yeah, gated, yeah, all kinds of methods. I cannot track all of them. And the way they work is they kind of do some modification of the backpropagation. You know, for backpropagation, what you're doing is basically propagating the gradients all the way back to the input features, right? But instead of taking gradients, by complaining that gradients are very local and sometimes the value itself is very important instead of the local variations. For example, when a function is like constantly 1 instead of 0, then probably that input is contributing something to the next layer and so on. So that's sort of intuition. So they modify gradient in a funny way, and then they do the backpropagation with some broken gradients, and eventually gets some attribution in some intermediate feature layer or in the input space. Yeah, I won't really deal with them in the lecture because it's very hard to explain what the explanation is showing. And yeah, I personally don't want to talk too much about what I don't understand. And the other drawback is that for new types of DNN layers, you always need to kind of figure out how to compute the backpropagation, this modified backpropagation. So for example, for transformers, you need to sometimes just skip one of the layer norm, for example, because there's not a very good intuition yet for how to modify the backpropagation in the right way across layer norm. And one strategy they just take is just to ignore this this layer norm layer and do the straight through backpropagation. If you remember that from the obfuscated gradient paper for defense. So you just ignore it and then just take the gradient as if the forward was just identity function. And sometimes the results depend on the implementation of the DNN. So this is one example where the mathematical formulation is identical for two networks, but the implementation is different. If you have two linear layers without any nonlinear activation in between, then it's the same when you just take W1 first and then W2. Oh, sorry. W1 should be, yeah, the ordering is wrong here actually. So if you take W1 on an input first and then you take W2 next, then it's the same thing as multiplying W1 and 2 first and then applying that matrix on your input. Okay, so mathematically they're identical, but because they are doing something interesting with the backpropagation, sometimes these two networks give different attributions for these methods. And I think this is a serious issue because then you don't have the uniqueness of your attribution score. So yeah, yeah, that's my opinion of these. But one caveat is that they're actually showing very good soundness results, especially for transformer architectures. So maybe there should be more understanding of why they are working and how they are working. Okay. So that's the kind of the summary of the method part. So linear models are providing nice contrastive explanations. And we also explore different ways of linearizing a complex model like DNN. And there are like two major different ways of doing it. So one is local linearization around an input X for the entire function F. Okay, so example of that was input gradients, smooth grad, integrated gradients, lime, sharp. But for the methods that use the notion of no information, like erasing an information completely for some features, the caveat was you need to kind of define what you mean by no information. Or the other way to introduce linearity in your model is to do global linearization for all X in the input space. But since if you do that for the entire function, then you're just going to have a linear function, right? So instead of doing that, they just take some part of the function to be linear and only focus on that part, trusting that the other part of the model is kind of well behaving in some way. So that includes CAM, for example, CAM or TCAF. And now, yeah, there are also different ways to aggregate features. You can also look at pixels, but also superpixels or instance segmentations, or even high-level concepts, which cannot really be represented as an aggregation of pixels. Yeah, you can also look at the feature map pixels as an aggregation of individual sliding window in the input space. Okay, so that was the first part, and let's take a break for 5 minutes. Okay, so probably let's get started. Okay, so I'm moving on to evaluation for attribution methods now. Why do we need evaluation if your model is, if your explanation method is supposed to be explaining your model, right? Yeah. So I feel like there's well, it's not my feeling, but there is a fundamental limitation of explainability. Soundness, explainability trade-off. So you cannot be, your explanation can be fully sound and also explainable, fully explainable. So there are two extremes. One extreme is actually your original model. And the reason why you needed a separate explanation in the first place for your model was because your model is way too complex. And so you need some kind of simplification of your model to make humans understand. But let's say a linear approximation, like if you linearize your model completely, then that makes your model interpretable again. But now the model is not the same model as before. So there's no way you can kind of look into the model in its own and still be able to understand what the model is doing. So this is a fundamental limitation of explainability. And therefore, if you look at different explainability methods, that they are sort of in the frontier, in the trade-off frontier between soundness and explainability. And there's no way you can say some explanation method is perfect by design. And eventually, what I think really matters is whether the explanation is serving my end goal and need. Okay. So there should be a way to kind of quantify that in numbers. So these are the usual requirements again that we talked about 2 lectures ago, I think, for explanations. So first one is, of course, soundness. Your attribution is basically figuring out what are the causes for your prediction. And the causes should be the true causes that, that leads to your prediction. But at the same time, for the sake of understandability, you need the explanation to be simple enough. For example, you should be citing fewer causes than there actually are. Yeah, the explanation should be applicable to many samples in your data set, for example. And relevance. If you have your final goal that you have in mind for applying your, for using your explanation for something else, then your explanation should also be serving your final need, final goal. That's relevance. Contrastive, ideally your model should be able to tell what is the response of the model when you change something from A to B. In other words, the foil needs to be clearly specified in your model, okay? Foil is the alternative kind of fact. Interactive, ideally, the explanation method should adapt to the explainee's knowledge and should take the explainee into account. So it should not always be like citing the most likely cause, but also retrieving the causes that are interesting for the user and so on. They may not necessarily coincide. So now, of course, soundness is the most important criteria, I guess. It's also called faithfulness or correctness of your explanation. Yeah, and also if you ask domain experts, soundness is also very high on the list of desiderata they need from explainability. But we should always keep in mind that this is not the only criteria. Okay. And for measuring soundness, a lot of previous researchers have relied on qualitative evaluation. Let's think for a moment whether that makes sense, right? So this is ICML 2017 paper, so this was quite long ago. And still then, the paper was not rejected for just making qualitative evaluations. This is what they said. Notice that integrated gradients are better than input gradients at reflecting distinctive features of the input image. Okay, so, and they show gradients and input gradients. The question is, can we really conclude that from those images? Okay. Well, for example, I do see those water beams, right? And I don't actually see that here. So yeah, maybe integrated gradients is delineating the objects a little bit better than gradients. But does that really mean they're actually reflecting what models are looking at better? Okay, that's a different question. So here's another example from the same paper. They say, we observed that the results make intuitive sense. For example, so this is German to English translation for language model. Und is mostly attributed to and morgen is mostly attributed to morgen. But I mean, to humans, it makes sense, right? But maybe the model was looking at a different feature for predicting those words. So if you keep relying on human intuition for measuring this kind of evaluation, explainability, then how can you actually detect models that are also relying on a new kind of knowledge that humans have not learned before, right? There's no way we can do it. So this is a case of confirmation bias, I would say, where the performance of your explanation method is confirmed against what humans think should be the right attention, right attribution. And this is another example from the CAM paper, 2016. And here they show a bunch of CAM visualizations from GoogleNet, VGG, AlexNet, GoogleNet, network in network, and then compare against the backpropagation variants like these ones and say, look, CAM is doing better than backpropagation approach. But here we're curious, what do you exactly mean by we're doing better? Okay, and we wonder if that's another case of confirmation bias. And yeah, the same here. Well, it is the same comment here, right? Yeah, can you actually conclude that? And what they eventually do for evaluation, quantitative evaluation, is they measure the number of times their attribution score map is corresponding to the actual object bounding box. I think what they did was take the 20% of the max value here as your binary score map, and then you draw the tightest box around it, and then measure the intersectional reunion between that box and the ground truth object box, and say when the IOU, or intersectional reunion, is greater than 50%, then that's a success, and you're measuring the success rate on the ImageNet validation set. And so this is exactly just comparing your score map against the ground truth location of the objects, and say, look, this so these are all CAM methods. So this CAM method is actually doing better than, so this is error, so lower is better than those backpropagation variants. So does that actually mean that the explanation is better for CAM than backpropagation or input gradients? I don't think so, because the model may have been looking at a non-object region to make the prediction. And if that was the case, then the explanation method, which has lower localization score, will actually might be explaining the model better than the other method. Okay. So So the conclusion here is that we should not evaluate according to our explanation when we are evaluating on explanation. Because it's not clear whether the explanation method, let's say we have this kind of image, input image, and let's say the cam for dog class was actually on the cat pixels. So we have two possible cases. So one is maybe the explanation method was complete failure, while the model was actually working right. The model was actually looking at the dog, but then your cam was kind of broken. Or it could be that your model was actually broken, and then your explanation method was doing the right job. Okay, and there's no way to tell these two cases apart. So these are typical pitfalls of soundness evaluation. So the soundness, again, is whether the score map is representing the true causes for model F to predict f of x. And therefore, a true explanation should depend on x, y, and f all together, rather than x and y, only x and y, for example. But when we are doing a qualitative evaluation, we are only looking at x and y to make evaluation and not the f. Okay, so that's in a sense wrong by design. And also, if we are comparing against ground truth localization, that is also not taking the model f into account. So that is by design wrong as well. But then we kind of see that that is wrong, but also it's a fundamental issue with evaluating explanations, meaning that there's no quick solution to that. Because if there was a ground truth explanation for some model, then that ground truth explanation itself is a good explanation, right? And there is no need to study what is a good explanation for a model and so on. So if there's ground truth, then there's no need to evaluate at all, right? So this is a chicken and egg problem. You should start from somewhere, but it's hard. So one trick that people have looked into was to look into something called necessary conditions for correct explanations. So there, people define a few criteria that a successful explanation method should satisfy without question, full stop. Okay. A good example of that was that an explanation S of fx must not contain any information if f, the model f, is not trained, is not a trained model. For example, it's a random initialization. If a model is just randomly initialized, how can an explanation contain any interesting information, right? Because if that is the case, then that kind of means your explanation is rather trying to please human evaluators or qualitative evaluations by producing plausible explanations. Yes.
Maybe I'm thinking a bit in the wrong direction, but is this always true, for example, for conclusion neural networks? I think it's known that if you just take a random initialized form and do like appearance on some image and do like a linear classifier out of it, you get better results than just using random guessing just because of some inductive bias in the model architecture.
Yeah, that is true. So yeah, there are results saying if you just randomly initialize a CNN, you're still gonna encode some inductive bias of let's say natural images. Yes.
Okay, yeah, probably not a problem. I mean, I guess still need to train a linear classifier for after we extract the features, and that's probably not the case. Yeah, but
But I also agree that probably this is way too strong, actually. So maybe there is some information contained in the score map, but somehow I think the main point here is that the score map should depend on the function f, the model f in some way. If it turns out that your kind of score map is independent of your model altogether, then something is wrong. I think that's the main point. So yeah, again, this was a bit strong. I agree, and probably I'll change the wording here. So, and this is actually what I meant by random initialized model. So it's not like your explanation should be information less when a model is randomly initialized. It's more like even if okay, when your model is changing, for example, when your model gets slowly if your model becomes randomly initialized model gradually from a trained model, then you should actually see some changes in your attribution map. Okay. So for example, the original explanation column here means your trained model. And now you're doing cascading randomization from top to bottom layers, meaning that you're gradually making logic layer, mix 7C layer, and so on as random initialization. Okay, so eventually at the rightmost column, you're going to see the results for fully randomized weights. Okay. And one interesting thing here is that for guided backpropagation, you see the same attribution map all the way through. So this guided backpropagation looks like it does not take the model F into account at all, because even if the model is changing a lot, like it's not a very small change. It's a global change of the model from a fully trained model to a random model. And even so, you're not actually seeing any change, maybe slight changes, but one nice thing that this guided backpropagation was selling themselves was that they get very nice visualization of objects when they compute guided backpropagation. And yeah, you get very nice results here, but at the same time, it's not changing, right? It's not really reflecting what the model is doing, in other words. On the other hand, you see some changes in gradient or smooth gradient, actually. Actually, smooth grad is doing pretty good job here because you're gradually moving from some more clear image here into a complete noise at the end. Yes.
So I don't understand how, for example, this guided backpropagation can sort of sell their methods by saying that it has nice visualizations. Because, I mean, if we were just to apply an edge detector, we get nice visualizations, but it's completely worthless. And I mean, to me, it seems like the method does exactly this. It injects human knowledge about what should be pleasing, and it doesn't take the model into account.
Yeah, but that kind of insight is kind of obvious when you look back, but at the time when they're kind of developing a new way to tweak your backpropagation in some different way, it actually looked like a very groundbreaking technology, because no one has done it before at the time. And then also, if you just look at the results, they look like a classifier has all the knowledge where the object is and so on. And so it actually looked like a very promising technology. But after 1-2 years, people gradually realized, okay, this is not actually working. This is not actually containing any information. Yeah. Yes.
Like voice guidance, for example, maybe it depends on the architecture itself, but not So we are choosing a lot of functions, and that's why it doesn't change. We don't.
So can you repeat your question? Sorry.
So now we are only changing the model parameters
Right,
based
yeah.
to random number, but we are not changing the architecture of the model at all. So maybe
Yeah.
this guidance depends on the architecture, and since the architecture doesn't change, it doesn't change also what's guidance.
Oh, okay, so guided backpropagation means you're adding a bit more guidance during backpropagation. So I can explain a bit more of what guided backpropagation does. So you know ReLU function, right? Non-linearity, right? And then during backpropagation, what happens is when your pre-activation value was negative, then you do not backpropagate, right? You just give 0 score. And if the pre-activation was positive, then you just let the gradient through. But what guided backpropagation does is you further do not let the gradient through when the backpropagation is negative. So in a sense, you're taking value on the gradient as well. And then during backpropagation, so it's an end condition. If your gradient is positive and your pre-activation was positive, then you let the gradient through. Okay. No understanding I have why this works, but that's what they did and named guided backpropagation. And it doesn't work actually.
So it's not related with the architecture.
I don't think so, yeah. It's just related to ReLU activation, yeah. And the reason why this is a necessary condition is because any explanation method, even the dumbest one, should satisfy it. If it does not satisfy even this test, then there's no way you can actually use this method at all in the future. So this is bare minimum test that every valid explanation should pass. And for even this bare minimum test, actually a lot of methods are not passing the test. This guided GradCam is also not passing the test. So guided GradCam is just multiplication of the guided backpropagation score map times the CAM score map. So yeah, of course, it inherits a lot of issues with the guided backpropagation. Yeah, otherwise we do not see sufficient ground to really say the method is not working. So I think this test is only rejecting guided backpropagation variance. The other test they had was, okay, yeah. So I explained all of that already in the previous slide. The other test they did was to compare two models. So instead of just randomizing the weights, they train with random labels instead. Okay, so the original model is trained with true labels, but the control group is a model trained with random labels. And again, for guided backpropagation, you're actually seeing the shape 0. So this is MNIST. Shape 0 for the model that is just trained with random labels. And so regardless of the actual content of the image, it seems to kind of give you a good edge detection of the input image. And actually, if you look at, yeah, this is also integrated gradients are also kind of showing some 0 shape, which is not good, but also understandable, because if you remember what integrated gradient does is it's multiplying your final gradient-based attribution with the pixel values, or the pixel value for the current image minus the baseline. the baseline in this case is obviously 0, the black image, because this is MNIST. And therefore, if you multiply with this 0 image, then, or image with 0, right, then you're going to see 0. Okay. And same is true for integrated gradient smooth grad or gradient times input, because these are also heavily dependent on the input. And this is also kind of showing that any method that is trying to multiply input on the score map is kind of weird, because even for these cases where you should not be attributing to any meaningful pixels, you're still attributing to something, okay? And seeing some patterns here, which is just dependent on the raw input image. Whereas gradient-based methods or GradCam look a little bit more random. And so we can probably say they passed the test a little bit better than the other methods. The other evaluation they did was how much correlation they see between the upper rows and bottom rows for each method. So for example, what is most impressive here is that GradCam doesn't seem to show any correlation between the explanation for models trained with true labels versus the models trained for random labels. The rank correlation for the pixels is almost 0. So CAM, I should say like CAM and smooth grads are kind of perceived in general as still the best explanation methods in general, I'd say. Maybe I'm wrong, but that's my current reading of current papers. Okay. So again, soundness evaluation is very difficult because there's no ground truth, right? But actually, if you think more, if you be more creative, you can actually simulate samples where the ground truth explanation actually exists. Okay, so in other words, for those images, for sure, I know where the model should be looking at, and I'm going to check if the model is looking at that. Okay, so this is also the paper from Bean Kim from Google, this teacup paper actually, and they devised this kind of evaluation where they have 3 classes: zebra, cat, and cucumber. And instead of just showing the image, they consider putting a caption at the left bottom corner. So maybe for the model, it's much easier to just read the caption rather than to recognize what's in the image, okay? So this is also kind of a feature selection problem, right? But we introduce a very prominent feature that the model cannot resist looking at, and we just measure if the attribution method is correctly picking that up in the models. And here, to show the impact, we introduce this noise parameter P between 0 and 1, meaning that if P is 0, then you're not, well, you're including this caption, but you decorrelate the caption with the image. And if P is 1, then your caption is always corresponding to the image, and therefore it becomes a stronger cue for recognition. Okay. And these are the results. So on the first row, you see the images without captions. So yeah, there's caption here, but I think this is kind of typo. So wrong image. So they're actually, those models are trained without captions. And now these are images with super strong captions. So caption is giving all the information that you need for this model. And yeah, this is again the model where the caption is not giving you a lot of information. Okay, so if you look at different explanation methods now, so we expect the attribution to be focused on the caption for the second row. And it looks like there's no quantitative quantification of that, but it looks like smooth grad is doing that most prominently. Although, again, the gradient-based explanations are not well calibrated. So depending on how you renormalize it, you may actually be able to get such a strong attribution to the caption for other gradient values, gradient maps as well. So I don't fully trust those kind of score maps, to be honest. But at least from the way they show it, it looks like smooth grad is attributing the most to the caption part. And therefore, their conclusion is smooth grad is doing pretty well here. Okay. Right. So that was another trick. And then we talk about this remove and predict way of measuring, which is very popular in explanation evaluation nowadays. So if you think about explanation again, it's a heat map, right, of the given input or the feature map. And that is giving you a ranking of each feature in some input or feature. And now, if the model is correctly citing the causes in the right order of importance, then, for example, removing the most important feature will greatly decrease the correctness of the prediction, because that was the important cue for prediction. And so by removing that feature, you expect the correctness of the model to drop a lot. And the same goes for the second highest ranking feature, and third highest, and so on. So in other words, you try to gradually remove information according to the importance dictated by your explanation heat map. Okay, gradually from 10%, 30%, 70%, and 90%, and see how much drop you see in your classification performance. Yes.
And remove just means select to zero. Sorry.
Right, yeah. So for images, the most popular choice here for removing is just gray pixels, which is close to mean value in the data set. Right. And yes.
Do we start with removing the pixels that should be explaining the result, or from the other end?
Okay, there are different versions of it. So you can start removing the pixels that are most important versus least important. So if you're removing the most important ones, then you should see a very quick drop in accuracy.
Yeah,
Exactly, yeah. And if you're removing the least important ones, then you should see the constant accuracy, right? But there's also the other way around. You're sometimes slowly introducing the most important pixels, and then you should also see a quick increase in your accuracy. And if you're introducing the least important pixels slowly, then you should see a slow increase in your accuracy.
basically, anything worse is just the orientation of the plot.
Yeah. And sometimes they also take the average of all these four and so on. So like 4 different versions. But I think the most popular one is just removing the most likely pixels and see how much drop you see. So so this is an example of the plot that you see. So you always compare against the baseline, which is randomly erasing any pixel in the image. Because, of course, if you're removing some pixels, then you should see a drop in accuracy, right? But the aim is to see even greater decrease in accuracy compared to random erasing. So here the metric, for example, is the relative drop in accuracy when erasing according to the attribution method of interest compared to random erasing. Okay. So of course, random erasing will stay 1 throughout the percentage that are erased. But for different methods, you're going to see a huge drop in accuracy in the first few top K erasing. whereas some other methods will see a smaller drop in accuracy, meaning that probably those pixels were not the most important ones. Okay, and based on that, you basically need your method to be kind of achieving even quicker drop in accuracy when you remove pixels. Okay, and therefore the curve with the that are kind of enveloping the others from below, they are supposed to be better explanation method. Sometimes you also measure the area on the curve for this plot. This is a normalized plot, but also you just take a look at unnormalized one where you do not necessarily compare against the random baseline. Okay. I think that's part of the exercise for the second exercise. Yes.
You have an explanation whether you get worse than random erasing was 75% and higher.
Yeah, so maybe maybe the next slide will probably explain that. Okay. So because we talked about it already, right? Like what do we exactly mean by erasing information? And filling in gray pixels or black pixels like here is probably not the best way to remove information. Okay, so there's original image here, but this is nicely named as missing misspice in a very recent paper. And let's say you erase some pixels here. Then actually what the model sees now is a crossword in this image. Yeah. So what does that mean, right? That means introducing black pixels does not necessarily just remove information, but it can actually add new information into the model. And so I think when you're actually only removing information by erasing pixels, then you should definitely see the random baseline as the worst case removing strategy. But I think the reason why you're kind of seeing these irregularities here is because the model is probably predicting something different when you're erasing in a more orderly fashion, for example. Because if you're erasing according to CAM or some explanation method that makes sense, then you're going to see something like that on the right side. But if you're erasing at random, then you're looking at something like this. And probably depending on different models, they might see different success rates depending on the pattern of erasing. Okay, so it's still kind of hard to explain what exactly is happening here, but but yeah, that could be one explanation of what's happening. So this slide means the remove and classify is again not the perfect evaluation metric, but this is currently what is the most popular and still perceived as one of the best ways to just measure soundness of explanations. Okay, but again, soundness is not the end of the story, and of course there are many other criteria, and I like to touch a little bit upon the relevance. So yeah,
but the erasing information thing, so the state of the art for erasing information is very loud at the moment. Or what would that be?
So I'm not sure if there's a common understanding of what the state of the art for this is. But my guess is probably in painting is probably the best way to do this. But again, like introducing an in-painting algorithm for evaluation it's like opening a can of worms again. So everything has pros and cons here. Yeah. So now there was soundness bit, and now let's actually look at the relevance bit. I think this is very important because we are not looking at explanation methods for the sake of itself, but rather treat them as an intermediate step towards the final goal at the end. for example, you can use the explanation for debugging the models. For example, identify spurious correlations and fix them, improve generalization to out of distribution, figure out why the model has made a mistake and then fix it, okay? Or understanding as the end goal. Do humans understand the idiosyncrasies of a model? Like if the model is doing something weird, then understanding why it's doing it and so on itself could be an interesting objective for humans. Or if the model is kind of doing something new that the humans were not able to do at the beginning, then probably transferring that knowledge to human is also very nice in itself. And also it may be needed for enhancing human confidence, right? So does it, like a lot of doctors are still very averse to machine learning based advices and so on, because they don't really trust them, but will introducing this explanation help them convert to machine learning based doctors? Or will that also convince people to use self-driving cars, although probably the safety is the same, right? So the question is if the soundness metric is fully aligned with those criteria. To tell you the conclusion first, it doesn't seem to be like that, right? So given an explanation, we still have some different end goals. Like for a machine learning engineer, they care about how to fix a model based on the explanation. Scientists might be interested in understanding further. Doctors need more trust. Yeah, soundness is just focusing on this intermediate step. And maybe we need some evaluation with the end goal in mind, okay? And when it comes to end goals, these are usually tied to human subjects. And so there's no way we can go around human in the loop evaluation eventually at some point. So this paper is what I cannot predict, I do not understand, a human-centered evaluation framework for explainability methods. This is a super nice paper that was quite recent. I forgot to add this year information, 2021, I think. And here, what they do is they try to see whether the explanations are actually helping humans or not. So this is the framework for their evaluation. They have human here, and what they do is they train humans with this data. So they have triplets of input image, explanation of a model, and the output of the model. And then they train themselves over K triplets, okay? And the task for human later on is to see what's going to be the output of the model to predict whether the model, for example, if the model is kind of making mistake on this image, then the human should be able to exactly pinpoint what is the mistake that the model is going to make, okay? And to make this kind of more meaningful, they mixed 50-50 percentage of cases where the model was correct and the model was incorrect. So to make it more meaningful. Okay, and eventually how humans are evaluated later on. Well, it's human evaluation, but eventually it's also measuring the effectiveness of your explanations. So this is the human prediction after looking at K samples, okay? And you measure the number of times the human prediction of the model output is correct. And you compare that against the human predictions when they have not looked at the explanations at all, okay? So this is exactly kind of factoring out the contribution of explanations for educating humans how the model is doing the job. So for example, for this wolf versus husky task, you're looking at the utility K. So ideally, the utility should be higher than 1, right? Because your explanation should be helping in some way. And the x-axis here is the training examples. So of course, with more training examples, you see further gain in human knowledge of what the model should be doing. In this case, Cam is doing pretty good job, right? So again, the same story. Cam is pretty good. Smooth Grad is also doing quite well. I'm kind of emphasizing Smooth Grad here because in the next task, you're also going to see that Smooth Grad is doing a pretty good job. So now this is like using machine learning strategy to educate humans. For example, humans do not know how to distinguish these different leaf types. And by showing where the model is actually looking at, human is also learning how to make classification. Okay, and in this case, Cam was helping a little bit less ideally compared to, let's say, Smooth Grad, the purple line here. Okay, and also their conclusion is that Smooth Grad is doing a good job for this task. And this is an interesting correlation plot for the utility versus faithfulness. So faithfulness again is the soundness evaluation, and what this is showing is that these two metrics are not correlated at all. So if what you care about is how humans interpret this and how humans gain knowledge from explanations, then soundness evaluation is probably not the best way to do it. And yeah, there are some final slides, but yeah, maybe we can quickly go over them in the next lecture and call it a day. Okay.